Okay, hello everyone. Today we are very pleased to have Theo Rakarchinas here. Theo is an assistant professor at University of Wisconsin-Madison, where his work has already won many awards, including a recent Amazon Research Award. Today he will be telling us about using machine learning for data cleaning. It's all yours now.
Thanks, Gaia. Thank you for coming to the talk, and thank you for having me over. So I'll talk to you about recent work that I have been doing and my group has been doing on how we can really follow a different perspective on analyzing and managing noisy data. And the core idea that we will be using there is that of statistical learning. I'll call it machine learning for the sake of being relevant. So you all know, I don't have to convince you, that more and more applications rely on analyzing tons of data. Like we are in the zettabyte era now because we want to be able to use all these amazing AI tools. And all these data-hungry applications are very prevalent, but they consume a variety of different data coming from sensors, coming from IoT devices, wearable devices, and machine-generated data and logs. And, well, we have to analyze all this data, but there is a catch. There are errors actually in all of these types. There's errors everywhere. So, for instance, for sensors, we can have noisy measurements, and we can have failures of these sensors. For video and unstructured data like natural language, we can have uncertain extractions, or we can have semantic ambiguity. For wearable devices or different connected vehicles, we can have actually adversarial examples, so you have noise that is injected with the purpose of having a malfunction further down the pipeline. And of course, we have human errors everywhere, especially in machine data. You can imagine that somebody is pushing code and they didn't check the commit, and now you have like bugs and errors coming in, right? So errors are everywhere, and in fact, I will claim that errors and low-quality data is actually the Achilles heel of modern analytics. And this has been observed by many analyses. For instance, this graph here shows that actually domain experts and analysts, they spend 60% of their time just collecting and cleaning up data to be used in downstream analytics and AI projects. Designing machine learning models and designing analytical models is becoming more and more streamlined with libraries like TensorFlow, PyTorch, or even more recent results like Ludwig from Uber. It's just drag and drop, right? So there are many modern systems that have appeared in the database and data management research that try to address exactly this problem of low quality. So, you have academic systems like HoloClean, which I'll talk about today, and Snorkel from Stanford. Google has this data validation library for TensorFlow. Amazon has DQ, that is, again, monitoring system basically for data quality problems in ML pipelines. So there is a lot of work around this area of develop systems that can safeguard basically your pipelines against low quality and erroneous data. However, in my work, I want to answer, as an academic, I want to answer a simple question, which is fundamental, which is, what is an appropriate and formal framework for managing noisy data? And I will put two constraints here. One is that I want a very simple framework, and I want a framework that can generalize to a bunch of different problems in analyzing data quality. So what I'm going to talk to you about today is a little bit, I'm going to start with some background on what noise means, what are the types of errors, what are the types of quality problems that one observes in real world data, and how people have tried to address these problems in the past. And then I'm going to introduce actually the theory core of all the systems that I have been building the last few years, which is this probabilistic unclean databases framework. And then I'm going to show you how you can actually rely on this theoretical framework to build useful systems for a bunch of data quality problems. So let's start with the first part. By the way, feel free to interrupt me at any point. If you have questions, let's make it interactive. So what is noise in data? So let's start with this simple example. This is a snippet from a data set released by the city of Chicago. It has to do with inspections of restaurants. And you can see a bunch of different problems. So DBA name was supposed to be a key, but now you have a different value for the same restaurant. You have typos about the city. You have different conflicting zip codes for the same establishment. And in general, these data sets sometimes, they don't come alone, but you may have constraints that try to describe what should the correct instance look like, right? Integrity constraints like functional dependencies. So you have a variety of different problems in real-life data, and the computational problems you want to solve, given such a noisy input and potentially a collection of domain knowledge constraints, is how do I identify errors in this data set? How do I fix these errors? And basically, how do I do, in this scenario for database people, consistent query answering over this data set, or for machine learning researchers, robust machine learning models? How do I do this thing? These are the types of computational problems. So people have actually, in the database community, people have studied this problem. And in fact, even the very first paper by Code was talking about how do we handle null values, right? So we wanted to safeguard against inconsistencies in our data. And in this case, for instance, if I have this unclean database and my integrity constraints, I can talk not necessarily about erroneous data, but inconsistencies. So the errors here correspond to either tuples or cells that basically introduce instances that violate these constraints. And these types of inconsistencies are very typical in data integration scenarios, in ETL workloads where I'm extracting information from different sources and I'm trying to canonicalize everything, right? And people have proposed to address these problems, people have proposed this framework of data repairs. So it's a theoretical framework that tells us how to cope with this inconsistent databases. And the target computational problem these people wanted to solve is that of consistent query answering. For instance, if I want to find all the distinct cities from this snippet, I should only get Chicago, not Chicago. Okay? So the tool that allows people to deal with these types of inconsistencies was to define a different database, that of a clean version of the noisy instance that you have, and that would be the repaired database. This is a slide from actually an authority in the space of data repairs. And the way you wanted to solve this problem is to find an instance that has, think of it as like the minimum edit distance, where edit here is in quotes because there are different definitions of edit, the minimum distance from that initial instance that you saw. So you want to basically perform the minimum number of transformations in your data set and get a consistent version. And you can now try to see, can I answer queries on that consistent version? And there are a bunch of different types of these types of repairs, and a bunch of theoretical results here that all have to do with tractability and repair taking, and can I do consistent query answering given different types of definitions of repairs, and so on and so forth. But I don't have to convince you that none of these things actually made it in any product and are not really used in practice. Very limited adoption. And the reason why there is limited adoption, let me convince you with an example. If I have this data set, you see that I have a bunch of errors. I have knowledge about my constraints. I can actually convert this data set into what we would call a consistent data set by deleting the first tuple. Now, this is a repaired database. I don't have any violations of these constraints on the FDs that I have. However, what I just did here is to remove the correct tuple. And not only that, I actually have errors that persist. These two errors, the typo, the obvious typo, is not fixed just by enforcing the integrity of these constraints. And I actually went and I have non-obvious errors. This 609 is actually the wrong zip code, and now my integrity constraints are not powerful enough to capture that fact. So, and I can use different variations of this type of repair, but all of them will actually have similar problems. So people try to address this by going away from minimality into that of the land of statistics. So they started thinking of, okay, let's think of these tuples as noisy observations of what the real tuples should be, and associate the probability with each of these tuples. For instance, the first one is correct, true, with a probability 0.9, the third one with 0.4, and the last one with 0.8, and so on and so forth. And then the goal there is to actually find the most probable world, given that I want to enforce this integrity with respect to my constraints. So it becomes an inference problem that I want to solve. From a practical, so in this case, the optimization objective is I can now, given that I have the constraints, I can start removing tuples or performing different edits in my data set to find basically to maximize the likelihood of these tuples. And there are different ways that you can do that. The problem, the big fundamental problem here from a practical perspective is how on earth do I know these probabilities to be able to reason about this world, right? So it becomes a learning problem now that I don't have access to these probabilities. Yeah.
So semantically, the probability should be like the probability that it is correct,
yes.
Or the okay.
So in this framework, it is the probability that it is correct. In our framework, we can give you, we will talk about the distribution over the exact values. Yeah. And in fact, I will show you how you don't even need any training data. You can learn these probabilities. You can reason about these probabilities just given these as input. So in our work, we're trying to come up again with a theoretical framework that can give you guarantees on the output of any algorithm that we will design to deal with noise. And we want to be able, we remember our requirement, it has to be practical. And I'll show you why our approach is practical. So we follow a very simple approach that has been actually very powerful in a bunch of other techniques, that of a noisy channel. How many of you know the noisy channel model? Oh, only Bessa? So what is the noisy channel model? The noisy channel model assumes that you have a clean version of your world, and then it goes through a process that introduces errors, and all you observe is basically the erroneous version, the unclean version. This is, and your goal now becomes, given that I observe that noisy version, I want to just find the correct world, the most probable correct world. Applications of this is every time you actually type something in your phone or your laptop and you make a mistake, a typo, and the spell checker fixes that, it's an application of this model. So spelling correction, part of speech tagging, machine translation, all these are NLP applications where actually this noisy channel model is the framework, the theoretical framework behind having all these practical applications. So motivated by this, we developed a framework that relies on this idea of a noisy channel for data cleaning, for managing and repairing and cleaning noisy data. So what is our framework? We start with a clean data source, and we assume it goes through this noisy channel, and we observe our errors. Because we want to design a probabilistic framework to understand, to really capture inherently and model inherently the notion of noise. Probabilities give you that is the right tool here. So what we assume is that we have some generating process, is a random process that gives us a clean version of our data. You can think of it as, the randomness is the fact that a Starbucks appeared in a specific corner of the street and not another corner, right? That's the real world process that is happening. You have what we call a noise generator. We will refer to it as the realizer. This is our noisy channel. This is again a robust, a random process that injects errors. And what you observe is just this process operates over a sample of your initial process, and what you get back is a final dirty database. So given this description, you can now start instantiating these two distributions, basically. So one is a conditional distribution. This is a generating distribution. You can instantiate these two to reason about what is happening in the dirty database that you're observing. So, for instance, if I want to model how correct data should be generated, I can do that by enforcing a certain probability over my raw correct tables. And then I can also have another component that tries to capture exactly the fact that integrity constraints should hold in the clean version. Integrity constraints are not, while they have been used as as a tool to find errors, they should actually hold in the clean version, right? So it's kind of a logical bias towards consistency. And for my noisy channel, I assume, as I mentioned, a conditional probability distribution that operates over a clean instance of a database. And then what we really have is a distribution over the possible swaps. Just to give you some examples of errors that you can capture using these models by putting these things together. For instance, if you want to capture duplicates, so my clean version was this, and now I want to model how duplicates are generated. The orange part here tells me basically, together with the green, tells me that the probability that an adversary will add the clean tuples is separate from the probability that I will actually go and add an artificial tuple, the red one up there, that was not in my real world. So we can model the generation of duplicate data. At the same time, we can also model errors due to transformations. So in this scenario, if I have a typo for Madison or the wrong zip code, all I'm saying is that I took the original clean data set and I multiplied with a probability that I will swap the two values for something else. What this does effectively is that it separates the cause of errors from basically how these errors change features in the underlying data distribution. And I'll show you what are the interesting problems that you can answer now over this frame. So think of it as basically I have the distribution that generates the correct data, and I just pass that through a conditional distribution that generates my errors. So we want to split these two. So what are the problems here? The first one is, first of all, what is the input? The input, we will only have the noisy data. We assume no information about these two distributions at all, which is practical because in real life, all you have is just a dirty data set. The first problem is to say, okay, if I knew anything about these two distributions, so imagine I will talk about learning them, but if I knew them, can I actually correct the errors? If I know the process in which correct data is generated and in which errors are introduced, can I change, can I fix that noisy instance J that I'm observing? So I want basically to find the most probable instance I that given these two distributions would actually give me what I am seeing. That's the first computational problem. The second computational problem is I want to answer queries directly on the noisy data set and get answers with guarantees as if I had actually asked these queries over the clean database. And the most interesting problem is, okay, can I actually learn these without any training data? And I want to just use J to learn basically these two distributions. Notice that if we have access to this, we have built this spell checker that is running on your phone for NLP. We have done exactly the same thing for your relational data.
What's the intuition for getting the number 3?
Number 3 is that noise is bounded. Hence what you're observing, and I will talk about that, hence what you're observing in your final version. We talked a bit about it. It has redundancy and bounded amount of noise. Therefore, you can actually recover what is the correct value for the different values in your data set. Think of it, the equivalent would be in robust statistics. Instead of taking the mean, I would take the median. So now I don't need to go and clean my data set. I will just take the median, and it comes with certain guarantees given a certain type of noise. It's similar to that. Okay, so this is basically the framework a theoretical framework that we introduced last year to describe what cleaning really means, motivated by the noisy channel and motivated by applications from like in the Chicago data set, you would see zip codes being wrong it wasn't a typo. The real reason why it was wrong, actually, if you were to dig into the data, would be that it was actually right on the boundary of 2 zip codes. And instead of this 609, 608, it's actually because it's right on the boundary. These are data. This is data that was manually collected by inspectors, and probably the inspector didn't know that they switched boundaries. So this would be the form of the realizer. Okay, so given these problems, we have a bunch of theoretical results. I'll just go over them quickly. The first one is that we saw that whatever people have done in the past in terms of theory, it's actually subsumed by this model. So all these kind of minimality repairs, they can actually be explained as specific instances of our framework. So this framework is more general. We can capture these notions of edit distance, that I want to update the minimum number of tuples, or I want to edit the minimum number of cells in my database. And the most interesting one is that actually showing when cleaning is efficient. So as you would expect, in most cases we want to run inference, right? So that's a very expensive process. However, we showed recently that you can actually get guarantees that would give you exactly the information theoretic optimal result, would be the result of exact inference over this framework. And you can get that actually with approximation algorithms. So let me talk a little bit about these results, and then I'll move on to systems. So the setup here, if I'm to abstract cleaning completely and put it in a formal framework, I can view it as the following problem of statistical recovery. Imagine that you have a graph, and you know the different nodes should have certain labels, and the edges capture interactions between these nodes. And you have a bunch of labels for the different nodes, but you don't know the actual correct labels. What you're observing is some noisy assignment to the different nodes, and you're observing also parity constraints on the edges. And even these parity constraints can be wrong. So just an example, the nodes here in a data set can correspond to cells, and the value that I see is the label. The parity edges are basically information coming from constraints, right? The constraints could hold approximately. So our goal, which is exactly the same goal as data cleaning, is I want to recover the correct labeling for each of these nodes. So formally what you want is you want an algorithm that will find this approximate labeling, this estimate x hat, that will minimize your the worst case expected Hamming error. Why expected? Because you don't know how noise is being injected, right? I don't know how the adversary or the noisy channel is flipping these labels. But over all these possible noisy channels that I have, so overall over the different assumptions that I have for my noise, I want to minimize the error basically between what I'm going to get out of my algorithm and what the clean unknown noise was. So this is a standard problem in theory. It's called that of statistical recovery. There are results that demonstrate that the optimal thing to do here is treat this as a probabilistic model, run inference, marginal inference over each individual node, and take basically the mode of that distribution. The problem here is that actually this is a computationally expensive process. I cannot run inference. So people have proposed approximation algorithms for the binary case. What we saw is that actually you can get guarantees even if you have categorical labels. So now imagine in your cells in the database, you know the domain of an attribute like zip codes or cities. These are categorical variables. And if I have an algorithm that can give me guarantees for the previous problem in the space of categorical variables, I actually have an algorithm with formal theoretical guarantees for data cleaning. So what we showed is that you can actually get an algorithm that is efficient. It's an approximation algorithm because you cannot really get the information theoretic optimal. But it comes with guarantees depending on how many labels I have, k, basically, for my categorical random variables. And what is the density, basically the structure of the dependencies I have. So for a tree, we saw that our algorithm actually proceeds as follows. It's something very interesting and simple. You decompose an input into connected, basically, regions. And then you perform correlation clustering to find groups that should have the same value. And you assign that value to all the nodes within that group. And then you do afterwards one check to make sure that you have consistency across groups. So it relies on clustering-based correlation clustering results. The interesting thing is that this algorithm gives you guarantees as to P here is the probability of error that you have. And you can show that the lower this probability is and the lower your domain is, the better the guarantees for your algorithm. The interesting thing to notice for the general case is that actually the more noise I have, if I have a dense structure, actually, lots of redundancy in my data, this noise part will go down, so it drops significantly. So in terms of statistical guarantees, I am much better having lots of redundancy in structure in my data and lots of constraints. The problem is that in that case, actually, I can only do it for low tree width graphs. I can only get these results for when I have bounded structure. So you have these types of trade-offs that come in from statistics and for computational efficiency. But overall, what our framework is giving you, what these results, is that given a bunch of categorical labels, I need bounded noise. I need noise that should be bounded by this quantity to be able to recover. If I have more than that noise, actually any automated solution will fail, which is a powerful dichotomy to know, because now you can actually detect, in many cases, if any automated cleaning tool will actually work, or you actually need to involve the humans in the loop.
Clarification. So N is the number of cells in the table?
N will be the number of cells.
Okay.
K is how many labels I have for the categories that I have. And P is the probability there of noise.
I see. And Hamming error is by comparing two tables, the dirty one and the
exactly. And Hamming error is per cell.
I see.
Am I different? Am I the same?
I see. Okay.
So now, really, this result tells you that, okay, if I have large domains in that table, so think of it as I have super high entropy in a column, and I don't have any constraints, I cannot do anything. No automated cleaning tool, even if I use machine learning, even if I use anything, it won't work. I need a human to look at it. On the other hand, if I have a small domain and lots of repetition, I can actually fix it in an automated way, and I can get a formal guarantee of that. So all of our systems are basically designed around this dichotomy. Any questions on that? Cool. Okay, one more theoretical parenthesis, and then to the systems. We saw actually here that that's an interesting result, that we saw that in many cases, if you have now this type of bounded noise, I want to know this P, I want to know all these statistical properties of my dataset, you can actually learn them even without training examples, as long as the type of noise, the adversary, and the amount of noise injected by the adversary is bounded. So I enable up to epsilon errors in my dataset, epsilon % of errors. So it's kind of a knob that says, from all these cells in my dataset, if 30% is corrupted, then I can potentially learn the correct model directly without having any label data. Okay? So you can use this result together with the inference results just to describe the types of guarantees that the models obtain. Okay, so how do we use this framework in practice, and what are the systems that we have built around this idea of when can we perform automated cleaning versus when we really need to bring humans in the loop? The very first system that we built, and in fact, the system that initiated this entire line of work, is HoloClean. So HoloClean is the first practical probabilistic data repairing engine. And until now, it's state of the art, at least the new version that we have improved our results. But really our first exploration was just trying to basically model the intention part of this noisy channel model, which was how do I generate my clean data? Forget my noise. I know that certain things are wrong, so I don't care now about how noise was injected because you have told me this is actually a wrong value. I want to learn the distribution of how the clean data is generated so that I go and basically fix it. Fixing here is I can treat it as empty and I can impute it, right? So what we do in HoloClean, we casted this problem as inference over a structured model, a factor graph. A factor graph is basically nothing more than saying that each of all these cells is a variable for which I need to make a decision, what is the correct value. And all I need to do is use my integrity constraints and other properties of the data set to enforce an alignment across these different values. So I want to enforce a joint state for all these different random variables. So in this case, for instance, I can have constraints like C1 here that corresponds to a zip code to determine the city, which couples the fields of two tuples that they should be in agreement with respect to this constraint. Or in other cases, I should respect the natural co-occurrences that are happening in the data set. I should never go and suggest Wisconsin as the state of Chicago, because I never saw that co-occurrence happening in the data set. Okay? So this complex model actually, these models really how the clean data generating distribution, so the generating distribution for the clean data, how it should be modeled. And then all we need to do is run inference over that. We cannot. It's expensive, right? It's SRP complete to actually get this inference. So back then we did a bunch of approximation tricks to be able to perform inference by pruning large domains. So we wanted to minimize that K that I showed you. And we also wanted to relax these constraints to have relational features. Turns out that actually both of these options are very well explained by what our theoretical analysis tells us now. So the most interesting thing in HoloClean was basically how do we make these constraints, these things scale. And again, we relied on this notion of bounded noise. So if I have bounded noise and I want to enforce this joint state in my world, I don't have to go and enumerate all possible worlds and check their validity. I can rely on the fact that the initial world that I have seen is somewhat close to the state that I'm looking for. And what you can do using this intuition is that you can break these complex constraints. So the constraint that creates problems is this one. Because think of a functional dependency. I want to enforce it over any pair of tuples. I will actually have this kind of structure being instantiated for all pairs of tuples that I have in my data set. So it's a complete graph, and I'm basically dead. So how do I break this? Remember, I assume that the initial table is the correct one, and I just convert these global constraints to local constraints. So I will assume that basically the assignment for the city for tuple 1 should actually not violate the assignment of another tuple, the actual initial value of that other tuple. So in aggregate, you can see that if I start enumerating overall the tuples that I have in my data set, what you see there is that if I have bounded noise, most of these features, most of these assignments will actually have the correct value, and I will be able to enforce this type of constraint in a noisy way. However, breaking these constraints and having these relaxed factors, and I can do this with different weights and different parameters for the different directions of the constraint. Right? I can do it for the zip code, so that I want zip codes that are compatible with whatever I have seen in my initial set. I want cities that are compatible with whatever zip codes I had seen in my initial set. And given that I may have different noise levels at different attributes, I actually have different weights for this model. So this is the relaxed type of model that we're learning. In reality, this corresponds to a logistic regression model with an interesting coupling of the weights. So it's very fast. And back then, it would yeah. Yes.
So what is it about the probabilities here that would suggest that I shouldn't just change the address of T1 to 3466 South Morgan Street, or something else that would actually make the zip code okay? Or
so this case, it's really the different co-occurrences that you have with the. I skipped the DBA name and other fields here. If you remember, the original set had keys and other things. So it's these types of dependencies that tell you that this street address actually corresponds to that key, and so on and so forth.
I'm just wondering how many degrees of freedom there are in practice in these cases, and whether you've got enough, whether you've got enough information from the probability distribution to steer you to
that's
the right answer.
Remember this?
Yeah. Okay. So it depends on.
So it depends on the structure. If I don't have any structure, all the attributes are independent. I cannot use that context to fix anything. The best thing I can tell you is take the most frequent value or take the median or the mean. The question is that we want to build systems that will tell you that without going and performing cleaning at all. Immediately you'll see that profile, and then given that you have enough structure and enough constraints to not have so many degrees of freedom, then you want to perform automated cleaning.
So that structure is what? It's pairwise correlations of columns, or because it's not. Yeah. First of all, functional dependencies are a little weird because in real databases they almost hold but not quite, and so even using it as a constraint can be problematic.
I agree.
And then, but what you often do have are a lot of attribute correlations, which are hard to capture.
If you bear with me until towards the end of the talk, I will show you exactly what is the structure that we want. It's basically the structure is, think of deterministic structures that would tell me attribute the address is kind of a function, a deterministic function of these other combination of columns. If I have this type of structure, I don't need to learn the actual function, but now I can use machine learning to find that mapping. So we want this deterministic, they're not causal structures, but they relate to structural models, basically. And I'll show you exactly how we can find these structures later in the talk. So HoloClean worked. The interesting thing for us here is that actually back then we were using a probabilistic inference engine, so okay, it runs faster. But the interesting thing is that it was actually more accurate than running Gibbs sampling on the full graph, which makes sense because Gibbs sampling wouldn't necessarily converge to the correct solution. But having this relaxed model and under the assumption of bounded noise, you actually get the correct distribution. Yes?
Is there anything else that one can do from the practical point of view? I mean, of course, it will not have any guarantees, but like when you build a factor graph with all the cities and all the zip codes, maybe you could kind of use some learning to say that I will build it only for the top 5 zip codes that are more probable according to this model.
So this is this
kind
idea.
of prune the space. Yeah, okay. So,
we are using the prune.
Yeah, okay.
So we would do very naive filtering conditions based on naive Bayes to prune basically find the most probable values, and then we would build the factor graph over these values. Okay. This is with pruning. So these are both with pruning. The problem there is that really the functional dependency style of constraints, they lead to a model for which approximate inference really won't convert. It needs an exponential number of steps. And if it gets to a minimum, there is no way of turning back. Also, I should tell you that we don't use these models anymore. We have moved away from these to like actual very interesting deep learning models that I can talk about them offline and that rely on attention and learning that structure on the fly. Okay, so that was learning the distribution. HoloClean wants to learn the distribution of the clean data. We have this other system called HoloDetect for detecting errors that again focuses on learning the noisy channel. So we learn a separate part of this PUD model now. So the whole idea there is I want to learn this realizer, but learning that realizer, if I want to teach, I'll take the most interesting network out there, deep neural network. I need a lot of training examples. The reason, so the question there fundamentally is, how do I find training data to even learn this distribution? Again, we will rely on this notion of bounded noise. And our approach, what it does is thinking of error detection as a binary classification problem for which we have lots of heterogeneity and imbalance, and we want to generate training data. What we do is we analyze the input data set, and we will learn a very simple model through program synthesis as to how errors are injected. We will rely on some annotations from the user, a very small number of annotations. For instance, here the user would say, you know what, for tuple 3, it shouldn't be Chicago, Illinois. The city, the correct value for city, it was actually Chicago alone. So we use this information, labels from the user. Remember the condition, a very small number of labels. Learn transformations as to how noise is introduced. How does this noisy channel introduce errors? For instance, in this case, I can add the character to inject a typo. I can remove a character. I can exchange full sequences of characters. And we use this noisy channel that we have learned to perform what is called an ML data augmentation. So we would take these initial training sets together with data tuples from our original data set and go and introduce new examples. For instance, we would say, here is an example of an error. I can go and flip the business ID from Porter to EVP Coffee. That's a full exchange. So I applied this transformation. For the second one, for the city, I left it the same. So I had Chicago, I made it, I introduced another error, sorry. That example is flawed.
It's just the Italian spelling, right?
Sure.
In Italian would be pronounced.
So the inspector was probably Italian. So that's the approach is use program synthesis to learn these small errors and then train a model. These are some example transformations that we've learned from real data. So this is actually a benchmark data set where you have typos being injected by adding the character X. You see that the most prominent transformation it learns is X. I should changing everything to X. This is from the adult data set in UCI, that it has some naturally occurring errors. It learns that you actually, in many cases, people mix female with male. So the most prominent transformation is flipping these two values. And this was a data set, actually this is a data set from Berkeley about animals, and they have this column that talks about basically the animals in captivity that can take values RO or empty, and there is confusion between R and empty and R and O. So these transformations are learned directly from the input data set and some examples from humans. Yeah.
So to what extent can you learn those transformations in a general way? Because a lot of these are like typo generation, which hold probably true across many data sets, and flipping values from the same domain is also quite common.
So this doesn't require that you're in the same domain. This is the most general transformation. It says it restricts you in the sense that I want to flip the entire string. So go and learn a switch, basically.
Yeah, I was just thinking, can you get away with, without asking users to provide a small set of labels for that specific data set? Can you generalize it?
So in the paper, we actually have results where we saw that you can obtain these from using unsupervised methods and then take only the highly confident attributes, assignments of the network, and use these as examples and then run program synthesis and do that. So we have these, we have experiments in the paper that show that. What you're restricting here a lot is you're restricting your noisy channel model to only introduce these types of errors. this last one is quite generic, though. Like in this case, it learned that I can flip from the same domain. It could be that we didn't restrict it to be in the same domain. It just learned these errors. And then you train a machine learning model that takes into account a bunch of different statistical properties of the data set that have to do with the attribute level, representation of your data, tuple level, data set level, to just answer that binary classification problem. Is this cell value wrong or correct? So is it compatible with the distribution I'm learning or not? And what we find, which is interesting, is that actually our approach is much better than active learning. So active learning, because of the heterogeneity that you have in your data set, requires a lot of training examples to be able to pick up this information. And in fact, it gets stuck as well. However, doing this type of data augmentation strategy, even with a small number of examples, works very well in practice. So, and on average, what we observed across the data sets that we run experiments with is a 3x reduction in terms of the training data that you needed with respect to active learning, which makes this way more practical. Like for some data sets, that the noisy channel itself had repetition in terms of how errors were injected, specific typos. Imagine you join two tables and you have repetition in the typos and so on. Then actually with just a few examples, you pick it up right away. So that reveals the power of program synthesis for learning transformations in that field. And it's an interesting area that we're exploring further here. Now coming back to Phil's question about structure. I will still call them functional dependencies, but I will use the correct definition of functional dependencies. I don't want dependencies that hold in the instance. So I don't want any syntactically correct functional dependency. But I want to find dependencies that hold in the data generating distribution. So I want cases where, for instance, they say, some of these scenarios here, they say that the zip code is really determined by my address and my hospital name in this scenario. Or for this specific data set, actually, there is this, where is it? It's actually pruned. There is a column called state average, where it's a concatenation between measure and two other columns. So that is an explicit function. If I merge these two, I will get the last one. So now I can fix errors just by following that function. So we cast this problem of functional dependency as that of learning the structure behind that distribution, where the structure is limited to learning these types of projections. So it's actually a linear model. Think of an autoregressive model. These attributes should deterministically dictate the value of another attribute. And we have an approach that relies on robust statistics, robust covariance estimation by taking pairs of tuples, sampling pairs of tuples over the data set and computing differences. And under, again, a weak realizer, weak here means that, the amount of errors is bounded. You can actually show that you will get the correct covariance, and from the correct covariance, you can actually get this type of structures. So what these structures, this is like two data sets from UCI. So the interesting thing for this structural result is that you can do a bunch of things now for automating data prep. For instance, I don't need to run any machine learning model to do feature engineering. These are two UCI datasets. This is an obfuscated dataset about credit approval. And the target attribute for classification is like A15. I don't know what it means. But there are a bunch of papers that actually say that the most important one is A8 across a bunch of different machine learning models. All of them should be finding A8 as the most important one for classifying. So we actually find that by running this very cheap model. This runs extremely fast. So these very cheap models will tell you A8 should determine A15. The way to interpret this is A15 is equal to some function whose input is A8. I don't care about the actual function, what it is. A machine learning model will find that function, but I know this structure. And it finds additional structural properties across other attributes. The interesting thing is this: for mammography, you find severity of a mass is your target attribute. Directly from all these other features, it finds that margin and shape are the most important ones. In fact, according to a textbook in cancer medicine, These are the two most important features that actually medical doctors will rely on to give you the severity of each case. In terms of directionality, it's also interesting to see that RADS, BI-RADS, is an artificial assessment metric that doctors came up with to classify the severity of different patients. So you would expect that the actual severity should determine that artificially made assessment metric, which is exactly what our model says here. Severity determines BI-RADS. So in terms of directionality, this type of modeling can give you a bunch of interesting intuition as to what is happening in your data. So this is the type of structure that our models are picking up. And interestingly, if I have an entry there, that there is some structure based on this profiling mechanism, automated cleaning actually will work very, very well. So if we take that tool, split attributes across data sets, a bunch of different data sets, as they have a dependency based on the model or they have no dependency, we're running imputation here, so I cannot reveal the name of that because it's under review. This is our state-of-the-art technique for imputation. But we're also comparing it against XGBoost. It can actually give you insights as to when will automated imputation based on really state-of-the-art machine learning models will even work. So if I have structure, you can see that I'm way more accurate. If I don't have structure, I'm actually not that accurate, which is exactly an instantiation of what our theory told us. Does this answer your question on structure?
It helps. It's an approach.
I don't want to know what the function is. I cannot tell you what the function is, but I really want to know if there is some deterministic dependency. The next step for this is actually to apply to query optimization and see if it can help find better models for selectivity estimation and all these things. Okay, just to summarize, so what we've done, what I have been doing in the last few years, is really go from theory around this type of new noisy channel model for explaining how errors are injected in real data to building actually systems that map, that learn parts of this process. And HoloDetect can tell you what is the noisy channel model to identify errors. HoloClean can tell you what should be the real generating distribution of the clean data. AutoFD gives you a profile of that, and so on and so forth. So we have this formal model, and basically we're building systems, data cleaning systems over this. Just to mention one connection, and then I can talk about it offline, it actually has exciting connections to robust machine learning. Using exactly this approach and the notion of structure, we have results that will be soon under submission that many of the state-of-the-art techniques that rely on robust mean estimation and robust covariance estimations actually, and just removing samples from when you're training a model can be improved if we're trying to correct a model. So we have that ready. And also we have a system that you can put as a filter in any predictive pipeline. And if there is a noisy data set, we'll always give you a guarantee that you will get either the same performance by running, if you were to run a machine learning model downstream, you'll either get the same performance as if you were not to perform any cleaning, or if there is enough structure, you'll always be better. Okay, so with that, I'd like to thank you for attending, and I'd be happy to answer any questions that you have around these systems. Yes?
So Theo, what do you recommend in general, like when we build models, especially like in machine learning, people are so used to the fact that there's going to be noise in the features, there's going to be noise in the labels, and we kind of have built these models thinking about that, you know. Now, say we repair the data, the real world data is still going to come with noise.
Yes.
And do you kind of recommend repairing the test data as well, like the real world data as well, and repairing the model in a way that it now thinks about the clean data?
We don't. What I recommend and what I recommend. Okay, I cannot recommend anything there. But I will. What I see happening, especially in the experiments that we have and the deployments in some companies. You don't change the model. You want your model to be robust to different types of noise because that introduces regularization and introduces all these interesting properties that you don't want to lose. What you want is a filter to avoid catastrophic, basically feature changes. So just to give you an analogy with training, let's focus on training first, and then I'll tell you about test deployment. For training, what people have done and what people have been striving for, and like even now, is like, let me build a mechanism that I will detect an anomaly that is not easy to detect and remove that training point. What if that training point, if it is a multi-attribute field, is actually wrong just because of one attribute that you can actually fix because you have enough redundancy in your data, which would make it easier to detect. So if you can do that with guarantees, you actually increase the sample of clean points that you have, and your model will learn better. So you want to be a little bit judicious as to how you're throwing and filtering data away. That's the only change that we are proposing based on these results. So when you're doing training, just instead of just throwing away data, try to fix them first. In fact, I'm working, you know Christos Zamos probably. So we're working together to show that actually you can get much better guarantees in the case of truncated statistics and in the case of like robust estimators. If you perform that decoding, basically. It has connections with coding theory, I can tell you about. For deployment, what we want is, so you can detect that there is noise in your input data that you're feeding into a machine learning model and turn off the pipeline, right? So you have down service. So your services go down, your recommendations go down, or you're willing to take a hit and survive with whatever recommendations have gone haywire. If I have trained a cleaning model or a filter that not only can tell me this is wrong, hence stop, versus this is wrong, and I think I can fix it, and you put it as a very thin filter before feeding the data into the predictive model, you can actually show that you will get, you will basically have your services be running and you don't have downtime. So what we are doing with this is if I have a model that can fix things, and I have learned it as long as the distributions don't shift and change rapidly, then you can use it in production as a filtering mechanism to basically recover. The equivalent would be really error correcting codes. There is a very strong connection there. So if I know that I can decode, given the types of noise I have, if I know that I can decode efficiently, I should decode and recover the signal and run. If I cannot do it, or if I cannot decode with guarantees, but I can detect that something is wrong, there are two different actions I can take. If I can detect something is wrong, maybe I give you a red flag. Otherwise, I don't intervene with anything, and it's somebody else's job, not the automated system's job. So that's how I see the world with respect to robust ML specifically.
What's your perspective on the role of people and humans in the pipelines that you talk about? Is it fully automated, or should a human developer be looking at the cleaning models that your system comes up with?
Nobody trusts any fully automated. Let me say that. What you want, though, is you want to prioritize the cases that they are looking at until you convince them that whatever the model is saying is actually correct. Just to give you some anecdotal evidence from deployments of our systems, there is this company that was doing basically categorization. So they wanted to find the canonical representation of things. And they had manual ground truth. So they gave us the ground truth. They told us, learn the model. It took them like months to create that. It took us 10 hours to actually train something and be able to deploy automatically. And we got an accuracy of 97% based on their ground truth. The ground truth, though, the 3% that we were in disagreement, 70% turns out it was actually the ground truth was wrong. Our system was correct. Because these systems, they have a more holistic view of what is happening in the data than humans. You will never convince somebody to trust that, though. But what you can do is that if the model now is super confident about something, you can actually provide, surface that to the user with evidence as to why the model is super confident. And that is a problem we haven't touched at all until now. It connects to provenance and clustering examples and so on and so forth. Yeah.
Okay, so let's thank the speakers.
Thank you.